Hey guys, alright, in this video we're going to work through questions 1 and 2. You will get extra credit if you decide to do these questions as well. I have already typed the equations into my calculator, so obviously most of y'all have submitted your calculators already. You can just follow along with mine. So it says fish are entering the lake at a rate modeled by this equation. So these are my fish that are entering the lake. Okay, then notice that down here we have fish leaving the lake at a rate modeled by. Okay, so these are the fish that are going to leave the lake. Then it says they're both measured in fish per hour. So this is in fish per hour. This one is in fish per hour. Okay, then the other thing that it says is in hours since midnight, t equals 0. Part A, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. So first thing that I would do is think about, I want to know how many fish. My equations are in fish per hour. That means that part A, you should have done an integral from 0 to 5, and then I'd be using the E of t equation, because I want to know how many are entering the lake. So I have already typed these equations in here, so I'm just going to do math 9. I'm going to go from 0 to 5 of y1 dx, and I got 153.4576. So 153.4576, which is approximately 153 fish, part B. Then it says, what is the average number of fish that leave the lake per hour over the 5-hour period? So notice, I want the average fish per hour. I already have fish per hour. So this is the 1 over b minus a integral a to b. So I'd have 1 over 5 minus 0. Then I want to know how many are leaving, so that's my L of t from 0 to 5. Okay, so then in the calculator, I'm going to work the integral first. So 0 to 5, this is going to be my second function, my y2 dx. Then once I get that answer, I'm just going to remember to go back and divide it by 5. So I get 6.0590. 6.0590. Now this one does not ask me to round it, so I'm going to leave it as fish per hour. Okay, part C. At what time for 0 less than t less than 8 is the greatest number of fish in the lake? Okay, greatest number, that means that I want to know an absolute maximum number of fish. So in my calculator, I'm going to look at my window first. I'm going to make it from 0 to 8. And then the second thing that I'm going to do is go into my table and see where my y values are. So it looks like they're in the 20s and 30s. So when I go into my window, I'm going to make my y's go maybe up to, let's just say 80, and see if we have the whole graph with that. So there's my first equation. Here's my second equation. Now notice that the first graph was the in equation, the second graph was the out equation. So I'm going to sketch this graph on my paper real quick so that I can label it. So for part C, here's my in graph, and here's my out graph. Okay, so I want you to think about, if I want the absolute max, I need the rate of fish to change from positive to negative. Okay, well think about, on this interval from here to here, overall, the number of fish that are entering is greater than the number that are leaving. So overall, number of fish in the lake is increasing. Okay, then on this side, from here to here, okay, I notice that my out has exceeded my in. So think about, if my fish are leaving faster than they're coming in, my L of t is greater. So that means that overall, the number of fish is decreasing. Okay, well then think about if the number of fish changes from increasing to decreasing, then overall we know that this point here serves as a relative maximum. Okay, now think about though the other rule. You can either set up a chart or you can conclude that it's the absolute max by claiming that it's the only one, which we see that these graphs only cross once on that interval. So this is a relative max, but it's also the absolute max because it's the only relative extrema on the interval. So I need to find this point. So second trace, option number 5, enter, enter, enter. They cross at t equals 6.2035. So I'm going to put, I have a relative maximum at t equals 6.2035, and that would be hours, because the number of fish in the lake, let's say, changes from increasing to decreasing. This is also the absolute minimum because there are no other relative extrema on 0 to 8. And so remember that if that's the only one, you automatically know that it's going to be the absolute max. Okay, you could have also done a Canada's chart there if you didn't state that. Okay, part D says, is the rate of change in the number of fish increasing or decreasing at 5 a.m. at t equals 5? Okay, well then at that point we'd have to take both of our rates and then take the derivative of those. So what I'm going to do first is I'm going to say, okay, part D, the rate of fish is, we're going to call it, let's call it R of t, okay? And it is going to be how fast they're entering minus how fast they're leaving. Hopefully that makes sense. So think about my overall rate of fish. We're going to just put the equations together as one interval. It's going to be how fast they're entering minus how fast they're leaving. I want to know if this rate of change, this overall rate of change, is increasing or decreasing. Well, then I need to take the derivative. So R prime of t is going to be E prime of t minus L prime of t. Or if you wanted, you could just go ahead and skip to I want R prime of 5. Well, then that'd be E of 5 prime minus L prime of 5. So in the calculator, really, probably you wouldn't have even written that. So overall, I'm going to do math 8 d dx of y1 at 5. Then I'm going to do minus. Then I'm going to do math 8 d dx of y2 at 5. And then I'm going to see it comes out to negative 10. So think about overall, okay, my rate came out to be negative. That means that overall the rate of the number of fish is decreasing. Okay, so I'm going to write that down here. So I got negative 10, 7,227. Okay, you also could have found these rates separately over here on the side, just found E prime of 5 and then found L prime of 5. If you wanted to do it separately, that would have been totally fine. So from there, we're going to state that the rate of change is decreasing because, let's say, E prime of 5 minus L prime of 5 is less than 0. So the rate of change overall is decreasing because when I take the derivative of E and L, I end up getting a negative value. And that's like the combined slope of those two things. Okay? All right, go ahead and turn for me, please, to number 2. Number 2 says the velocity of a particle moving along the x-axis is given by a differentiable function v of p, where Vp is measured in meters per hour, t is measured in hours. Then it says select values are in the table. The particle p is at the origin at time 0. So I'm going to put right here xp of 0 is 0. Because if he's at the origin, that means that his position is 0. Okay, part A says, explain why there must be at least one time from point 3 to 2.8 where v prime, which is the acceleration of the particle, equals 0. Okay, part A was a Rolle's value theorem. Rolle's value theorem says, I'll put it up here at the top. Rolle's theorem says that if f is differentiable and f of A and f of B are equal to each other, then there must be an x where f prime of x is 0. Now, this should make sense to you because think about it. If my graph is going to go from a y value to a matching y value, there are only 2 ways for that to happen. It could go like this, but if it's differentiable, then it can't do that. The other way for it to connect would be to do it like this. And if I have a smooth and connected curve in my graph, that means that at that point I'm going to have a 0 slope. Okay, so that's what Rolle's theorem says. So for part A, it says, we're going to say Rolle's theorem guarantees this. Rolle's theorem guarantees this because Vp of 0.3 equals 55 and Vp of 2.8 equals 55, and it is stated that Vp is differentiable. Okay, so Rolle's theorem says if my function is differentiable and my y values match each other, then automatically what they stated up here must be true. Okay, part B. Use a trapezoidal sum with 3 subintervals to approximate the value of the integral from 0 to 2.8 Vp of t dt. Okay, so potential for a mistake here, you were only supposed to do 3 subintervals. So if you went 1, 2, 3, 4, you would have ended up missing this, even if you did your trapezoidal rule correctly. So remember, trapezoidal rule, you're going to do a half in the front, then you're going to add the y values, so I'd have 0 plus 55. Then my width there, delta x, would be 0.3, because I'm going from 0 to 0.3 plus. Next one, I'm doing 55 plus negative 29. And then the delta x from 0.3 to 1.7 would be 1.4. That's my width on that next subinterval, 1.4. Okay, then for my third and final one, I have a 1/2 here in the front. Then I'm doing negative 29 plus 55. And then the width between those two, if I do 2.8 minus 1.7, I get 1.1 as my width. Okay, then I'm not even going to add it up. I'm just going to be like, check, boom, done. Okay, now part C. Part C says, second particle Q moves along the x-axis so that its velocity is given by, then we have an equation. Also, this is in meters per hour. Okay, so these are both velocities. Then it says, find the time interval during which the velocity of Q is at least 60 meters per hour. So in my y equals, I'm going to type my equation in here. Okay, so it says it was 45, then square root x, then cosine, then 0.063 x squared. Okay, just like that. So 45 root x cosine 0.063 up to the x squared. Okay. Then it says find the interval at which it's at least 60 meters per hour. So in my graph, I'm going to put 60 as my y2. Now the other thing I'm going to need to adjust is my interval. So it says here I'm really only going to be looking from 0 to 4. So for my window, I'm going to make this 0 to 4. And I'm just going to keep the y's the same and see if I can see the whole thing. Okay, so there's my graph. Okay, there's 60. So I can see that at these two values, my graph was above 60. Okay, so I'm going to sketch this right here. Okay, so for my graph, went like this. Here's 60. So then I want this interval right here where it says it has to be at least 60. So I'd want this interval right here. So let's find our intersection. Second, trace 5. Enter, enter, enter. The first one happens at 1.8661. The second one happens at, enter, enter, I'm going to guess it happens around 3.5191. Okay? So I'm going to put VQ of t equal to 60 at t equals 1.8661. 3.5191, and then it's going to be above 60 on that interval. So VQ of t greater than 60 on 1.8661, 3.5191. Okay? Now obviously you probably didn't have to show this much work for you to get points. Then it says find the distance traveled by the particle on the interval when it was at least 60. So remember that for distance traveled you had to use absolute value bars. Absolute value bars. So in my calculator I'm going to do math 9. I'm going to go from the y values listed, 1.8661 to 3.5191, and then in here I'm going to insert my absolute value bars and then my y1 dx. Okay, so the particle would have traveled 106.10917. So I'm going to put distance equals the integral from 1.8661 to 3.5191, absolute value, VQ of t dt, and it was 106.1091. Okay? Alright, then part D. Okay, part D says, at time 0, particle Q is at position negative 90. Okay, so I'm going to write that down. My position of particle Q at 0 is negative 90. Then it says, using the results from part B and the function VQ from part C, find the approximate distance between the points at this time, 2.8. Okay, well, let's just think about it. If I know the position of particle Q at 0, it's at negative 90, then how can I find the position of particle Q at 2.8? This was a version B. So all that you had to do is say, okay, well, particle Q at 2.8 is wherever particle Q was at 0 plus the integral from 0 to 2.8 of the velocity for particle Q of t dt. Okay, then remember, I already know x of 0, they just gave it to me, it's negative 90 plus, and then this integral I'm going to work out in the calculator. Now, when I do that, remember that you should not have absolute values around it this time. Okay, so 0 to 2.8, alpha trace y1 dx. Okay, it comes out to be, think for 100 years, 135, 9376. You could have left it like that, or you could have went ahead and subtracted the 90 from it. So when I minus 90 from it, I got 45.9376. Okay? Now, that's only the position for particle Q. I also need to know the position for particle P. Okay, well, think about, when do I know the position for particle P? Look back up right here. It told me that x of P is 0. Okay? So, I already know that it's going to be xp of 0 plus the integral from 0 to, and actually, let's plug in our time value here. This should be a 2.8 here. To 2.8 of the velocity for particle P of t dt. Okay, well, think about, this is 0, but then this is the trapezoidal sum that you worked. Trapezoidal sum, okay, that you worked in part B. Now, I haven't added it up yet, but I'm going to go ahead and do it now. So I would have had 0.5 of 55 times 0.3 plus, 0.5 times 55 minus 29, then multiply that by 1.4 plus, then I would have had 0.5 negative 29 plus 55 times 1.1. And that gives me 40.75. Okay, so think about, if one of my particles is at a position of 40.9376 and the other particle is at 40.75, then how am I going to find the distance between the particles? All I have to do is subtract. So in my calculator, I'm going to take the position of particle 1, I'm going to minus the position of particle 2, oops, delete that, which was 40.75. And if I subtract those, I'm going to know how far apart they were. So they were about 5.1876 units apart. Okay. So I'm going to go ahead and squeeze this in this bottom little corner right here. Distance apart is the position of 2.8 minus the position for particle P of 2.8, which is 5.1876. Okay, and that would have been your final answer for part D. Okay, good job.